Welcome, dear students, to the second half of the merge sort algorithm lecture. In the first half, we were talking about the merge sort algorithm. Uh, and in the merge sort algorithm, I give stress on the merge procedure, which is an important component of the merge sort algorithm. So before going to see the dry run of the merge sort algorithm or the merge procedure, let us see graphically how the pseudo code will actually work. So here is an example. We are going to deal with an array which is represented by A, and that is in unsorted form. And we are required to sort it out by using the merge procedure. For that, we need to divide it two into two sub-arrays, each about half of the elements. So for example, here we have 8 elements, so 4 elements are going to be in the left array, while the rest of the 4 elements are going to be part of the right array. Similarly, we need indexes. For example, for the left array, I am using the index I, which actually refers to the first element. And for the right array, I am using the index j, which also refers to the first element, to the element that is stored at the first location. We also need an index represented by k, which actually refers to the element of the first location of the given array. Okay, now the merge procedure is like this. Remember the two piles on the table? This is the first pile, this is the second pile. Both are in sorted form. So both are in sorted form. What we need to do is to actually compare the element or compare the cards that are at the top of each file. So the top element here is represented by I, while the top element of the R is represented by J. So in other words, compare the element stored at ith location with the element stored at the jth location. After comparison, we came to know that 1 is actually less than 2, or the element stored at the jth location is actually less than the element stored at the I location. So it means that you have to move this element to the kth location. So here you can see in the B. After comparison of I and j, we came to know that the element stored at the jth location is actually less. So you have to move it to the kth location. Once you have moved the element, you need to do two things. Increment the k counter and increment the j counter by 1. So now the key element the key variable refer or index refer to the next element, to the next location, that is 10. And the j index also refer to the element which is stored at the second location. Now recursive, do the same thing again. Compare the element at the ith location with the element at the jth location. After comparison, we came to know that these two elements are the same. So in that case, as I mentioned mentioned earlier, that once two elements are exactly the same, is up to you whether you want to move this element or this element, but we prefer to move the element at the left sub-array. So you have to move to the kth location, and then again you need to do two things: increment k by 1, and now you have to increment I by 1. So what does it mean? It means that once you remove an element from the left array, you have to increment the I. Once you remove an element from the right sub-array, you have to increment the j counter. Again the same thing, compare the element at the ith location with the element at the jth location. Now you have to compare 4 with 2. After comparison, we came to know that actually the element stored at this second location is small than the element which is stored here. So you have to move this element to the kth location. Okay, that is here. So once you move this element, the second thing you need to do is to increment this j index by 1. So now it will refer to the third element. Do the same thing again. Compare I with j. Compare the element stored at ith location with the element which is stored at the jth location. So after comparison, we came to know that 3 is actually smaller than 4. So we have to move this to the kth location. So here you can see we have moved it to the kth location. 3 has been moved to the kth location. And then do two things, increment k and increment j. So we have increment the k and we have increment the j. Now do the same thing, compare the left piles of card with the right piles of card, but only the cards at the top. So here the card at the top has been referred by I, while here the card at the top has been referred by j. Compare these two. After comparison, we came to know that 4 is actually less than 6. So we have to move this number, this element, this card from here to the kth location. After movement, you need to do two things, increment k by 1 and increment I by 1. And similar, you need to repeat the process for the rest of the element. And remember, one more thing, we have to insert a special value known as the sentinel value at the end of each subarray, and it will actually indicate the end of the subarray. So once the counter index either I or j move or reach to this sentinel value, for example here it is an indication that now this list, sublist or subarray has been completed. So you have to remove the elements from the other subarray, which in this case has been represented by L. So we will see, we will do the same thing by using the algorithm, the merge procedure, which is mentioned here. Okay, let me start the dry run, but before that, one suggestion is that once while you are practicing or while you are watching this video, please keep this algorithm in front of yourself, because I am going to use an online whiteboard, so I will not be able to come back here. Okay, but the recommendation is that once you are practicing or while you're watching this video, you have to keep this algorithm in front of you so that you can better understand the steps of the dry run. So let us start with the dry run. For that, I need to go to the live board, which is here, and this is the most craziest thing. So it will take some time to draw things, a bit complicated, but we'll try my best. So we have to consider the same example that we just saw. Okay, this is our ugly array. The elements of this array are 2, 4, 5, 7, 1, 2, 3, and 6. The name of this array is 1. The indexes of this array are started from 1. So we have a total of n elements, and n in this case is 8. Okay, so first step of the algorithm is n1. You can see it in the algorithm that n1 is equal to q minus p plus 1. So here we need to find the indexes first. So this is our p and this is r. The first index p, which is equal to 1, r is equal to 8 in this case, while q we need to find, and for that the formula is like the floor function. You can also take the ceiling, lower bound which is 1, index of the first and then 8 index of the last, which is 8, and then divide it by 2. Actually we will get 9 by 2, which will 4.5, and then finally you will get 4 from here. So the value of Q is 4, the value of R is 8, and the value of P is 1. Now put it here. Q, the value of Q is 4 minus the value of P, which in this case is 1, and plus 1. So plus 1 minus 1 cancel, and 1 is equal to 4. Now in step number 2 we need to find N2. N2 is equal to R minus P. Total number of element in the second sub-array. We are going to divide it into two sub-array. So from here we know that the value of R is 8 while the value of Q is 4. So 8 minus 4, you will get 4. So after division, we will see that the first sub-array will contain 4 elements while the second sub-array will contain also 4 elements. So in the first two steps, we are actually creating sub-arrays with elements n1 and n2. And n1 in this case is 4, while n2 in this case is also 4. So now we need to create the sub-arrays in step number 3. So for creating the sub-arrays, we are actually dealing with a loop, and the loop is starting from 1. I is less than or equal to n1, that is 4. I plus plus. Now check the condition. The value of I is 1. So 1 is less than or equal to 4. Yes, condition is true. Once the condition is true, we need to, this is actually step 3 and step 4. Then we need to go to step number 5. In step number 5, we need to assign the value to the left sub-array. So left sub-array 1, assign it the value of a p plus I minus 1. So the value of p is 1, the value of I is also 1 and minus 1. So they will cancel each other and we will get a of 1. So this is actually our left sub-array represented by L. I will show it here, will represented by L. So L1, this is L1. Assign L1 A1. So what is A1? That is 2. So 2 will be assigned to this location. Now we have for loop, so we need to go back here. Increment the value of I by 1. So previously the value of I was 1, the new value is 2. Again check the condition. 2 is less than 4. Yes, 2 is less than 4. Condition is true. Now you have to do the same thing. Assign Li. Now the value of I is 2. Assign L2. The value stored at A2. This is A, this is location 2. The value here is 4. Assign this value to L2. This is L, this is 2. We have an empty here. So assign 4 here. Again, for loop, go back, check the condition again. Now the value of I will become 3. Check the condition. 3 is less than 4. Yes, condition is true. Come here. Now the value of I is 3. So L3 is equal to A3. This is A, this is 3, the value here is 5. Assign this 5 to L3. So this is L3, assign it 5. Okay, go one step forward, go back to the loop, increment the value of I by 1. Now it is 4. 4 is less than 4? No, but 4 is equal to 4. Yes, the condition is true. So you have to go one step further. That is, assign L4 the value of A4. This is A, this is 4. The value here is 7. So assign L4 the value of 7. Again, we have a loop. Go back here. Check the condition. Now the value is 5. 5 is less than 4? No. Now the condition is false. Once the condition becomes false, we do not need to execute this step. Okay, so we have to go to the next step. I will change the board here. Yes. Add a new page. Okay. Now we have created a left array, and let me draw it again. The array, the original array was like this. The original array A with indexes 1, 2, 3, 4, 5, 6, 7, and 8. And the values were 2, 4, 5, 7, 1, 2, 3, and 6. Okay, and we have created a left array with the help of the steps of the merge procedure, and the left array was like this: 1, 2, 3, 1, 2, 3, 4. The values were 2, 4, 5, and 7. This is the first sub array. Okay, now we need to create another array, and that is going to happen in step number 6 and step number 7. So actually the steps are same. Step 6 and 7 are actually the same as the previous steps 4 and 5. What will happen? It will actually create a new array, this time with the name R, which stands for the right array. The same index is 1, 2, 3, 4, 5 is also there. Let me show you the algorithm for a moment, how we actually create these sub arrays. So you can see here in step number 3 we created two array L and R. Number of elements are 1, 2, and 1 plus 1. And 1, the size of n1 is 4. 4 plus 1, 5. So the indexes are 1 to 5. Similarly, we created a second sub array with the name R, and the indexes are from 1 to n2 plus 1. The size of n2 is 4. 4 plus 1 is 5. So 5 elements here, 5 elements here. That is how we create arrays, sub arrays in step number 3. And in step number 4 and 5, we saw that we have assigned the values to the left array, while in a similar way, now we have to assign the values to the right sub array. So this will happen in step number 6 and step number 7 in a similar way. So I will do it directly. So I have to assign the values. There is at location 5, which is 1, the value 2, 3, and 6, and then the condition will become false. So these things will happen in step number 6 and 7. Now step number 8 of the algorithm is simple. Let me show you. Step number 8 is simple. Left array n plus 1 mean 4 plus 1 mean 5. So assign L5 the sentinel value infinity. In a similar way, assign R n2 plus 1, that is 5, infinity. What does it mean? So n1 is, let me write here, n1 is actually 4, and the value of n2 is also 4. So step number 8 is that assign the left subarray position n1 plus 1 is equal to the sentinel value. Remember, we use it to indicate the end of the first pile and the second pile, or the end of the first subarray and the second subarray. And in a similar way, in step number 9, take the right subarray, and here we have n2 plus 1 equal to infinity. So you can see, and 1 is 4, 4 plus 1 is 5. So L5, this is L5. Assign the sentinel value. It will indicate the end. In a similar way, N2 is 4, 4 plus 1 is 5. R5, assign the sentinel value. Okay, this is happening in step number 8 and 9. Now, the merge actual things will start at step number 10. And it would be better to change the board once more. I will open a new page, a blank page actually. Well, it's important to draw the array because we will be dealing with them. Main array A having indexes 3, 5, 6, 7, 8. Then we have the left and right array 1, 2, 3, 4, 5, 2, 3. Put the values. Half of the values in the first half, sentinel value, half of the values here, this is left, right, 1, 3, 4, 5, 1, 2, 3. Okay, so step number 10. Now, if you remember, we are going to use 3 indexes: index I, index J, and index K. This is index I, index J, and index K. We saw these things in the example. Okay, so in step number 10, we need to initialize the indexes. I will take initial value of 1. In a similar way, in step number 11, the value of j will also be 1. Step number 2 is a bit technical because it has a loop. Step number 12 has a loop for k is equal to p to p to r. Change it. Okay, is equal to p to r. Okay, let us first check this condition by putting the values. The value of k is p, mean the initial value of k is 1. The starting value is 1 because p is 1, and then the final value is k is less than or equal to r. The value of r we know, the final value is 8 k plus plus. Okay, to check the value, check the condition. 1 is less than or equal to 8. The condition is true, so we need to go to step number 13. So in step number 13 we have to check an if condition. Remember, now we need to compare these two cards, the card at ith location and the card at jth location. And once we find the smallest value, we have to replace or we have to move that value to the kth location. So these are the things which are going to happen in these steps. In step number 13, if L I is less than or equal to right R J, if this is true, then you have to assign A of k the value from the left subarray. Assign A of k is equal to left. If the condition is false, then you have to go to the else portion. In the else, you have to do the opposite. The condition is false, then you have to assign the right subarray value to the k. Okay, now let us see the values and do the comparison. If Li, what is Li? This is L, this is I. What is the value here? That is 2. So 2 is less than or equal to Rj. This is R, this is R, and this is J, and the value here is 1. So compare. 2 is less than 1? No. 2 is equal to 1? No. So the condition is false. Once the condition is false, this statement will not be executed. We have to come to the else portion. In the else portion, what we need to do, we need to assign A of k. This is A, this is k, this is the value. What value we need to assign? Rj. This is R, this is J, and the value here is 1. So assign 1 here. I will remove it. remove this two, go back. We have assigned 1 here. Now it is in sorted form. One more thing, remember, once you remove a card from here, you have to increment this j by 1. So this will actually happen here. In the else, you have to increment the j. If it is the f portion, then you have to increment the I. So increment j by 1. Now j will point to the next element. That is element stored at the second location. Again, the same thing as we are dealing with the for loop. Come back here, increment k by 1. Now k previously was pointing to here. Now k will point to the next location, that is the element stored at location number 2. Okay, now here again do the same thing, compare li with rj. So li contain 2 while rj contain 3. So once you do the comparison here, that is 2 is less than or sorry, the value here is also 2. So 2 is less than or equal to 2, is not less than but is equal. So the condition now is true. Once the condition is true, you have to execute this statement. What's happening here? Assign a of k, that is a of k, which is 2. What we need to assign? Li. So assign this value, which is to this location. So the value here is 2. And do two things. Increment this I by 1, you see here. So previously I was pointing to the first, now it will point to the next element. And also you need to increment the k by 1. Now k will point to this location. Again, loop, go back, compare these two elements. As we know that 2 is less, so 2 will be replaced with this element, and then so on. As long as we have elements in these two sub arrays, the procedure will continue. Okay, so this you can take the rest of the steps, you can continue giving the dry run to this algorithm with the rest of the elements. So this is actually how we can apply the merge procedure. Remember, this is not the actual sorting algorithm. This is just the merge procedure, which is plays an important role in the merge sort algorithm itself. Now let us back to the lecture presentation. So this is the procedure, and we saw how it actually runs. Do some practice over the dry run. We also saw this example. And this is the actual merge sort algorithm. So if you see this algorithm, it actually recursively call the merge procedure for sorting the initial array, and then for sorting the first sub array, the left array, and then the right sub array. So in details, this merge procedure actually works as follow. First, we need to compute the length of the first sub array, and then the length of the second sub array in line number 1 and line number 2. And then we have to create these two sub array. The first sub array is called L, the second sub array is called R. In step number 4 to step number 7, we actually copies the element of the main array into these two sub arrays. The first half of the elements were assigned to the left array, and the second half of the elements were assigned to the right array. And we also assign the special value, sentinel value, to the last element of each sub array in step number 8 and step number 9. Then in step number 10 and 11, we initialize the indexes ij, and also we have an index k, which will actually refer to the original array first location, and these will actually refer to the sub arrays first locations. And then the comparison actually happened here. If the first element of the first sub array is less than the first element of the second sub array, then assign it to the k. Otherwise, assign the element of the second sub array to the kth location, and the process will continue for the rest of the elements. So this is how this merge procedure actually works. Okay, now this is another way to looking at the things. For example, how the merging actually take place from bottom up approach. We started from the base case where we have only one element, and then we merge them into two elements, and then we merge these two subarray to form another subarray of four elements, and then finally we merge the four element subarrays into the final sorted sequence. So this is how thing works in a bottom up approach. Now the analysis portion. Before analyzing the merge sort algorithm itself, it's important to understand how we actually analyze the divide and conquer based algorithms. Inside the analysis, we will use a term which is known as recurrence or recurrence equation. Actually, recurrence is a type of equation, or you can also say is a type of inequality that will describe itself in terms of its values on smaller inputs. Or you can say it is a function that is defined in terms of one or more base cases. So we saw that in the merge sort algorithm, we were actually dealing with a special case where we have only one element in the subarray, and that case is actually known as the base case. So here the recurrence actually means a function which will contain one or more base cases, and the base case is actually a stopping condition. And also the second property of the recurrence function is that is a function that will defined in terms of itself, recursive, recursion with smaller arguments, with smaller portion of the problems. So if these two properties, base case and calling itself, recursion, are present in a function, that is actually referred as a recurrence or recurrence equation. There are different methods by using which we can solve the recurrences. For example, we have the recursion tree method, which we will see in a moment for the analysis of the merge sort algorithm. But we also have the iteration method, and we also have the substitution method, and one of the mathematical method is known as the master theorem method. So different methods are available for solving the recurrences or recurrence equations. We will be focusing on the tree method for analysis purposes. Uh, Coming back to the analysis of the divide and conquer algorithm, it actually contains a recurrence call to itself, as I just mentioned, and we often describe its running time by a recurrence equation, and recurrence equations can be solved by different methods, and we will be using the tree method. Okay, for that, we actually need an equation. There is no need. We can actually prove this equation by using the master theorem, but we will not be using that. We are not interested in proving this equation. We are actually interested in using this equation for the analysis of the merge sort algorithm. But let me explain what this equation means. Let T of n be the running time of a problem, and the size is represented by n. So T is the running time, n is the size, and it is equal to this equation. Okay, so if the problem size is small enough, we can say that n is less than or equal to some constant c. So the straightforward solution will actually in this case will take a constant time, and that constant time has been represented by theta 1. So it actually this equation will take only a constant time 1 if we are dealing with a very small input. The input is less than a constant value c. In that case, the running time is constant, and it has been represented by theta 1. Now suppose that our division of the problem yields a subproblem represented by A. A actually represent a subproblem, and the size of this subproblem is 1 by B. Suppose that the size for my sort algorithm, to make things simple, we suppose that the size of A and B, they both are 2 or multiple of 2. So it takes time which is equal to n by b to solve one of the problem. suppose we have a problem, so we need to divide that problem into sub-problems. Now each sub-problem is represented by A, and the size of each sub-problem is 1 by B. So now we take a consideration that both A and B are actually 2, means we have to divide the problem into 2 sub-problems. So in that case, we actually need to write n by b. We can say that it will take n by b to solve one subproblem of size n by b. So the time taken to solve a subproblem having n by b is t n by b, and a is actually the number of subproblems which we have divided or derived from the main problem. So actually the time taken to solve one subproblem is equal to t n by b. So what is going to be the total problem, the total time? So the total time is that you need to multiply it. You need to multiply the time taken by each subproblem, which is represented by a. Once you multiply them, you will get the time taken for solving the whole problem. And also in this equation, we can see dn and cn. So the dn is the time for dividing the problem. As we can see, there are 3 steps in the divide and conquer approach. So this is actually the time taken for the division, and c is the time taken by the combine step, the third step. So this is the time taken by the first step, time taken by the third step, and this is actually the time taken by the second step, which is actually the conquer step, and it involves more technicality. So the divide, the number n represent the size, so divide time taken, the combined time taken, and actually represent the size again. So this is actually an equation which we can prove by master theorem, but that is not necessary and we do not require it. So in summary, if the problem size is very small, for example less than or equal to any constant value, in that case our total running time is going to be equal to 1, and that is the case for the base case. However, in other cases, we have to divide the problem into a sub problems. A is any number, we will consider it to be 2, and n by b is actually the size of the each sub problem. So if we have n time, then the sub problem is going to be n by 2, and for calculating the time of each subproblem, we need to multiply them with one another. So by keeping this equation in mind, we are going to see the analysis of the merge sort algorithm. Although the pseudocode of the merge sort works correctly when the number of elements is not even, but to make things simple, or to make things simplified, we assume that the original problem size is a power of 2. What does that mean? It means that each divide step of the algorithm will yield 2 subsequences of size exactly n divisible by 2, or n by 2. We reason as follows. To set up the recurrence of for t of n, the worst case running time of merge sort on n numbers. So merge sort is just on one single element. It will take a constant time, as we just saw, and that is theta 1. But when n is greater than one element, or once the n is larger, then we have to break down the running time of the algorithm. How we will divide that? So we need to follow the 3 steps approach. In the divide step, we just do a single thing, and that is to find the mid of the sub array, the mid item of the sub array, and we know that it will take constant time, so we can represent it by theta 1, and d of n, as we saw in this equation, is actually the division, and n represent the size. So if we want to divide the problem, we actually need to find the mid of the sub array, and that will take constant amount of time. In summary, the divide step of the merge sort algorithm take constant time, and that is represented by theta 1. In a similar way, let us first discuss the combine and then we will come to the concur step. In the combine step, we already noted that the merge procedure play an important role in the combine step. And the merge procedure work on n elements sub-array. So it will take a total amount of theta n. N again is the size. So the division step take constant time theta 1, while the combine step, which actually include the merge procedure which play an important role, will actually take larger time, that is theta n, and n is the number of the elements. So we can say that the combined step represented by C of n is equal to theta n. So remember, division is equal to theta 1, while the combine is equal to, the division is equal to theta 1 constant time, while the combine is equal to theta n. And also the concur step means to recursively solve the two sub-problems. Each one, as we again consider the power of 2, is size n by 2, which contributes to 2 times t n by 2. What does it mean? We have to divide the problem into two subproblem. Each subproblem will take time t n by 2. So the two subproblem will take 2 multiplied by t n by 2, as we saw in this equation. We have to multiply total number of subproblem, which in that case is 2, and total number of time taken by each subproblem, which in this case is n by 2. So multiply them both. Now to combine thing, we need to add the functions. So d of n and c of n can be added straightforwardly for the merge sort analysis. So we are adding a function that is having a value of theta 1 with a function that has value theta n. This sum is a linear function of n, that is theta n. So adding the 2t n by 2 term of the concur will give a recurrence of the form mentioned here. So once you add the things, this is going to be like this. How it comes, how this value comes in this equation? This is very simple. You need to add the three terms, that is dn, cn, and this concur step. But once you combine the dn with cn, that is theta 1 and theta n, remember the rule, we have to consider only the dominant term. So the dominant term here is theta n. So we will ignore theta 1 here. We will only consider the theta n. So d of n and c of n is combined. We ignore the lowered term and we consider the high order term, that is theta n. However, this is the concur step. And the concur step, as we see here, is 2t n by 2, 2 times t n by 2. So this is the concur step, and we combine the divide and the combine step here in this equation. If you apply this on the merge sort algorithm, which is mentioned here, so this step number 1 will actually take constant time, that is theta 1. And here we are actually finding the mid value. So remember, the division step will take a constant time, that is theta 1. So theta 1 here, theta 1 here. And this is actually the first sub array, second sub array. So this will take time if we consider a case of power of 2, n by 2 and n by 2. So once you combine these two, you will get 2 time capital T n by 2. And this is actually the merge sort where we combine the two solutions and this take theta n time. Once you combine them, you will get this equation, which is here. Now you can use the master theorem, which I do not want you to use, but you can use it to show that theta n is actually equal to n log n. This is something which we can prove by master theorem, but we will not do that. So just to remember that theta n is actually equal to n log of n, and here the log actually means log to the base 2, and n is actually the size. So here we have a logarithmic function, and we know that the logarithm functions grow more slowly as compared to the linear function n square, n cube, n quadratic, etc. So it's mean that the running time of this algorithm is going to be much more efficient as compared to the running time of other algorithms like insertion sort, like bubble sort, and so on, where the running time is n square, etc. So if we introduce the constant c, we can rewrite this equation like this. Theta 1 is a constant, so you can write simple c here, which represent a constant value. So the constant c represent the time required to solve problem of size 1. So if you have the base case, the time required is only c, which is a constant. And also here you can see that it is also the time per array element of the divide and conquer step. So here instead of writing theta n, we can actually write c of n. Now finally, if we draw the tree for the merge sort algorithm, is going to be like this. This is actually derived from the previous equation, the recurrence equation that is mentioned here. For convenience, we assume that n is exactly a power of 2, again an assumption. So here part A actually of the figure, it will show Tn, which we will expand in part 2 into an equivalent tree which representing the recurrence. So the term Cn is the root, here the root of the tree. This is how we draw a tree. The root is up here. So this is the root node, which is represented by Cn, and Cn is a constant. The cost incurred at the top level of the recurrence. And then we have two subtrees. We divide the problem into two subproblems. So we have two subtrees of the root. And they are actually two smaller recurrences and represented by n by 2, n by 2. Remember, n by 2. So we have 2 times. So if you combine them, you will get 2 times n by 2. And then in part C, it actually shows extended process carried out one step further by expanding the n by 2. Now if you expand this n by 2, you will get n by 4, n by 4. This is like we are actually minimizing the number of elements in each sub array. For example, the number of elements here are 8, so 4 will be here, 4 will be here. That is 8 by 2. Now you divide the 4 into sub list, so 2 elements will be here, 2 elements will be here. So that is like 8 by 4, you will get 2. So this is how division occurs. So in part C, we carried out one step further by expanding the n by 2. So the cost incurred at each of the two sub nodes, for example here, at the second level of the recursion is n by 2 or Cn by 2. So we continue expanding each node in the tree by breaking it into its constituent parts as determined by the recurrence until the problem size gets down to 1. So this is the process. We continue breaking down into subproblems unless we get to a situation where we will have only one node at each you can say the leaf nodes. So here what is important to note is the cost at each level. So for that at the root level we have the cost of C of Cn actually. So the top level has a total cost Cn. The next level down has a total cost of Cn by 2 plus Cn by 2. If you add them out, you will get C of n. The level after that has a total cost of Cn by 4 plus Cn by 4 plus Cn by 4 plus Cn by 4. If you add them out, you will get C of n at this level, and so on. In general, the level I below the top has 2 raised to the power I nodes, so each contributing to a cost of Cn divided by 2i, which will give you Cn, a general term at each level. This is level 0, level 1, level 2 up to level n. So at each level the cost is constant, that is Cn. Second thing is the total number of levels of this recursion tree. So remember, we can prove it, but we do not need to prove it. Just you need to remember that the the height of this tree is log of n plus 1. And again, n is the number of nodes, or you can say the leaves corresponding to the input size. So in an informal inductive argument, we can justify this claim by using an inductive method, but we will not do that. So here what is important to remember is that the height of this tree is log of n plus 1. So if you want to compute the total cost, the total running time of the merge sort algorithm, we simply need to add up the cost of all these levels. So the recursion tree has log of n plus 1 levels, and at each level the cost is Cn. So for a total cost, we need to multiply C of n with log of n plus 1. So once you multiply, you will get Cn log of n plus Cn. Now apply the rule. Ignore ignore the lowest term, which is C of n. Ignore it, you will remain Cn log of n. Now ignore the leading constant, which is Cn. So what is remaining is the constant here is C. Remove the constant C. What remains is n log n. So the worst case running time of the merge sort algorithm is actually n log n. And as we know that n log n algorithms, they are very efficient because the logarithm function grows very slowly. So that is why we can say that the merge sort algorithm is a better algorithm, efficient algorithm as compared to the previous algorithm. So this was a simple method by using the tree method. There are other methods as well, but we followed the tree method in order to analyze the merge sort algorithm. In summary, we have to find the cost of each level and also the height of the tree, which is equal to log of n plus 1. Or you can also simply consider log of n, doesn't matter, because we have to ignore the leading terms. We have to ignore the lowest terms, which in this case, we have to consider only the lowest term, which in this case is log n. So at each level, the cost is C of n, which is a constant, and then the height is log of n. So once you multiply, if you want to find the total cost, you have to add up the cost of all the levels, and then you have to multiply it. So you will get Cn multiplied by log of n plus 1. From here you will get Cn log n plus Cn. Ignore this term, ignore the leading constant, and what remains is the running time of the merge sort algorithm. So this was about the analysis of the merge sort algorithm. We have a midterm paper due for coming Saturday, and after that we will continue our course. So I will lead you with best wishes for the paper. See you. Goodbye.